Welcome, everyone, and thank you for being here today. My name is Pedro. This is my colleague Jan, who came all of the way from Germany to be here today. We both work at Siemens Cyber Defense Center. As for myself, I began at Siemens 2 years ago as a master thesis intern. I developed a proof of concept rules engine, and now I'm working mainly as a developer for a next generation detection platform that we are going to talk today. Jan, do you want to introduce yourself?
Do it later.
Yeah? Okay. So let me just adjust my microphone a little bit. Yeah, it's fine. So before we start, I want to talk a little bit about the Siemens Cyber Defense Center, our team, and what we do. So we are responsible for monitoring all of the Siemens infrastructure worldwide. What this roughly means is that we collect all of the data from the Siemens infrastructure in order to analyze it and detect security threats. The Siemens Cyber Defense Center is a joint venture between Germany, Portugal, and the United States. In Portugal, we are very proud to be the largest team. We are very motivated to drive Siemens cybersecurity topic forward. By the way, if you see someone wearing a shirt like mine with that unicorn over there, they are part of the Siemens Cyber Defense Center. We are located in Alfagide, in the outskirts of Lisbon, where we do a lot of cool activities, like we have little workshops on lock picking. We assemble our own 3D printer, and we have people with different interests, like we have little concerts on Wednesdays, and that is to say that we have a place for everyone. We also do other outdoor activities, like hunting for unicorns. No, not really, just playing paintball, but yeah, we'll do a lot of cool stuff. So what drove us to build a new detection platform? Siemens is a very large company located in more than 200 countries with more than 350,000 employees. And this translates to a very large volume of data that we need to analyze. Currently, we have about 60,000 events per second. Oops, my micro is falling. About 60,000 events per second at an average peak. And to further aggravate the issue, we are seeing that more and more attacks lately, and those attacks are being even more sophisticated. In 2016, 2,000 malware samples were identified each day on average, and this rate increased by 328 in 2017. And we want to fight back. We want to be able to detect more stuff and be able to increase our capabilities. But in order to do that, how can we efficiently scale our platform? How can we employ new techniques in this constantly changing environment in order to detect more stuff? And how can we quickly react once we identify a security threat? Before I dive into our new infrastructure, I want to talk about the old one. What did you have and why did we need it to change? So we started off with a pretty common setup nowadays. We have a CM instance with a set of rules and lists. Those lists can be white lists, black lists, indicators of compromise, and that all of our data from our infrastructure will be sent to this CM and be correlated. Once we detect something using the rule set, then a new alert is generated. But because our infrastructure is so large, we have a very large rule set. Our lists have millions of entries. We have a lot of events. One CM instance will not suffice. So we don't have one, we actually have 3 instances. And once we deployed this architecture, the problems started to become apparent. First of all, these CMs do not scale horizontally, meaning that the computations cannot be distributed across several machines. Our events are simply splitted across these 3 instances, meaning that if you want to make a calculation based on all of the events, we can't really do that on this platform. Moreover, this licensed software is a very closed box, and we cannot tailor it to our particular needs, and it doesn't offer really an API for us to automate things. So what this means is that every time we need to change a rule in one CM, we have to replicate this change on the other CMs. So besides the lack of scalability and flexibility, we have replicated data and replicated code. Moreover, every time someone needs to access this infrastructure, it has to access it via 3 access consoles. Moreover, to aggravate this problem, there is no really analytics and AI integration. So our goals was to build something that could be scalable. We needed to improve the overall performance of this old architecture. We need to improve the detection capabilities. And the solution really needed to be flexible, customizable, because we need to be able to detect new use cases, and if you can detect them, we simply change our solution to a new one. And of course, it also has to be cost effective. So we set out and we tried to build a new detection platform, and this is what it looks like. On the left side, right here on the log sources, are the network components and servers and sensors and everything that we need to monitor from our infrastructure, and they are sent to a set of collectors which parse those logs and forward them as an event. The first big change that we made was to add a message broker, in this case Kafka. Kafka was built by LinkedIn to transport massive amounts of data from one place to another, and this was very useful for us because we want to keep our events flowing. Moreover, Kafka is highly scalable, so it can easily handle our current throughput, and in the future, if we need to have more consumers and have more data, we can simply add a new server, and that's it. Kafka also allowed us to have several consumers consuming data directly from Kafka. What this means is that every time we need to build a new application, we don't need to configure all of the collectors to send data to that application. We simply send all of the data to Kafka, and then the application will simply read that data. The second change that we needed to make was to replace our CM with something new. The current commercial solutions didn't really offer all of the features that we needed, and the ones that offer the features that we needed lack flexibility for us to really tailor the solution to our particular needs. So instead, we set out and we built a new one, a new rules engine using Flink. With Flink's API, you can develop an application, and all of your computations and data can get distributed across a Flink server from our a Flink cluster with several servers. I will talk a little bit about Flink in later slides and this particular solution, but fundamentally, we were able to replace our CM with a distributed rules engine with the same rule set as our CM, and capable of generating the same alerts and where we could build the same use cases. Besides sending all of the events to this rule engine, we also send the events to the cloud. More specifically, we send the events to Athena, where they can be queried by our analysts, and this data can also be used by the machine learning algorithms to detect new use cases, which Jan will talk about next. Finally, all of our alerts are also sent to a distinct Flink job, which enriches the data and creates tickets for our analysts to triage. So I will talk a little bit about Flink. So what the heck is Flink? Many of you probably never heard about it, and those who did heard about it, maybe you don't know how it works or what it does. So basically, there are two ways to process a continuous stream of data. Okay, you can basically continues to gather a set of data, and once you have a bucket, you can process it, that finite set. So this is called the batch processing, or you can continuously process events as they come in. This is called stream processing. Flink was built as a real stream processor, as it can continuously process events and generate results. With Flink, you can build, you can program a direct acyclic graph to build your application. This graph can have a source node, which fetches data from the outside. You can have a set of operational nodes and a set of sync nodes to export data to the outside. As an example, you could, for instance, create a very simple Flink application, which the source will is simply reading data from a socket, which let's assume that are bytes which represent strings, and then you could have an operational node called a filter, which will forward events to the sync if a string contains the token evil. Right? The cool thing about this is that you can set a level of parallelism for a specific operator. For instance, if I set the parallelism to 2 for the filter node, this means that the source node can split its data to the 2 filter nodes that can process the events in parallel. So you can have 2 or more machines in a Flink cluster, and then this node will be replicated across these two machines. The data can be sent to both these nodes in parallel, and then the computations can be applied in parallel. And this is how we scale our applications. So why did we choose Apache Flink and not something else? First of all, Flink provides something called the exactly once semantics, which no other stream processing engine offered at the time. This means that if our application fails, when it recovers, it can recover exactly from where it was before the failure, with no duplicated data and no event loss. Moreover, it is scalable and offers low-level mechanisms to access event time, which, for instance, Esper cannot be distributed out of the box, and Storm does not offer such low-level mechanisms. We also have as an high availability solution, and it's very flexible. So we went out and built a distributed rules engine. I won't go into much detail about this engine. If you have questions, you can talk to me later, but I will give a general idea of how we build it and how you can build it yourself. So we basically have a source node that reads data from Kafka, and we started to build a static pipeline to detect a specific use case. For instance, you can build a filter to try to grab all of the events that represent user failed logins. And you can build this pipeline in order to try to understand if a user is trying to log in more than an X number of times to a specific machine and it's failing. And it can represent a malicious behavior, and we want to detect it. So we build this sample pipeline statically, which can be used to generate alerts. But we didn't want to have a static pipeline because we don't want to change the code to detect new use cases every time a new use case. We wanted to build a new use case. So instead, we found a way to dynamically compile code inside of these operators so that we can change their behavior. So we have created an event processing language that I'm going to talk about in the next slides, but our users can use this simple language to upload rules to a node that reads rules from Git and sends it to all of the nodes in Flink. And then when a node receives this rule, it is able to compile it and then dynamically apply a specific function of the rule to the incoming events. And this is how from a static pipeline, we change to a dynamic pipeline, and then we can have rules flowing in dynamically without having to stop and start the job. The good thing about this is that we can add a new server to the Flink cluster, and we don't need to restart anything, and it will simply be one more server that we can use, and then all of the rules are also dynamic, so there are no restarts required to make upgrades, to upload rules, and to do all sorts of things, which is really cool. So this is more or less how our event processing language looks like. You can create 3 types of rules: standard rules, data store rules, and aggregation rules. The standard rules are your just are simple match plus action. What this means is that it's search for specific tokens in an event, and when it finds them, it triggers an alert which can be enriched. The data store rule is very similar, but instead of triggering an alert, all of the events are forwarded to a data store. Then we have aggregation rules, which are a little bit more complex. So data aggregation rules can be used to aggregate events in time windows. So we can aggregate events for an arbitrary amount of time, and at the end you can apply a computation to all of those events. For instance, you can count how many events fall into that window, and if that count surpasses a certain threshold that you define, then an alert is generated. I have here a sample of a rule, of an aggregation rule, which was created using our own language. So you specify in the sources which types of events will be processed by this aggregation rule. In this case, we are processing VPN events. Then we have a filter function which searches for a specific token in these events. In this case, it's looking for session starts in the field name of an event. If it's a session start, then the event is further processed, otherwise it's discarded. Then we have here an aggregation window, which is aggregating session starts for 8 hours and then applying a computation every 30 minutes. And this is trying to look for an user that is trying to log to session start in distinct hosts. If he attempts to start a session in more than 2 hosts, then an alert is generated. Then we can enrich this alert by querying a data store, in this case to add more information regarding that user. So we will get a user ID, and then we'll query a data store and get its name and region, and then we can enrich the event with a certain message saying that we found the user on this region which was attempting to start a VPN session from multiple hosts. And that this is how we developed how we develop our use cases, and then these rules can then be injected into our rules engine. So I will give you the stage, Jan.
Thank you, Pedro. Can everybody hear me up there? Okay, perfect. So my name is Jan. I'm the Chief Data Scientist in the Cyber Defense Center of Siemens. My background is in artificial intelligence and in big data. I start the presentation with the statistics you have already heard from Pedro of the 2016-2017 strong increase of attacks in cybersecurity, actually. I would like to point to even one more statistics, and this statistics which shows you the time lag between initial attack to the containment. So which line is very important for us? It's the middle line here. So actually this line. Why it is important for us? Because 4 or 5 years ago, the big red bubbles here have been right in the middle. So from initial compromise to discovery, it took days or weeks sometimes. But today you have something like weeks, months, or even years. So why is it that way? So what we detected is that attacks today are much higher sophisticated and increasingly get automated. And we have to fight back with the same weapons, actually. Let me guide you through a well-known use case, through a well-known attack and how to fight it. So a large corporate network like the Siemens one is protected from the internet through a big firewall, a very powerful firewall. So this means basically you can create connection from the inside to outside and not vice versa. The same thing goes for malware, basically. So if a host is compromised inside the network, the malware tries to connect to its C2 host outside the corporate network on a regular basis. The C2 host itself tries to hide behind some kind of domain like imevil.com. That's a stupid name, right? But even if the name wouldn't be that obvious, it's never a good idea to hide behind only one domain, because at any time we would track the traffic and blacklist the domain and game over player one, right? So what does a malware? A malware keeps changing its domain continuously, like appending an index 01, 02, 03, and so on. Again, not a very good idea. It's too predictable. If it's 08, you would predict 09 and 10 and also on. So malware usually uses something like domain generation algorithms. This one is taken actually from Wikipedia. It's a very simple one. It's initialized with year, month, and day, and then it produces every day a new string, like the orange one on January 7th and the blue one on January 8th. You append a domain, register this domain, the top-level domain, you register the whole domain, and it's done. You have a connection. Okay, in reality, the algorithm is not that easy, and in reality, it's not that easy to distinguish between malicious domain and normal domains. On this slide, you see a mixture of normal domains, legitimate domains, and malicious domains, and you can try to find out which of these domains are really malicious. So I think the task is not easy here, right? So it's, by the way, not easy for any human. Human cognition is not made for things like this. It's not made for detecting things like this. So in fact, humans detect the malicious domains only by chance. So the orange ones are the malicious ones. All the other ones are legal domains, legitimate domains. They are the normal domains, including the very long one at the bottom of the slide. It's the name of a city in Wales, actually. That's the proof. That's the weather forecast on British TV. So, as we find out that humans are not able to distinguish the domains from normal domains, so we decided to bring AI to the fight. We took several approaches, actually. Some more traditional approaches on the most left-hand side here. So, you let some experts design statistical features on the domain name, like changes from vowel to consonants and similar statistical properties, feed it into a machine learning algorithm like a random forest or a gradient boosting machine or something like this, and check what happens. Can they distinguish DGAs from normal domains? And actually, here, the accuracy is not bad. It's 85%. It's actually better than any human could do. Next approach, you take an approach from natural language processing, actually more specifically from sentiment analysis. So if you type in your comments to Netflix on a movie or something like this, they do something like this. So they extract n-grams from a domain string, which means these are snippets from the domain string of length, of fixed length, 3, 4, or something like this. So we extract www, www, w.f, and so on and so on. You get approximately 54,000 of these features. You encode everything into a frequency vector, again feed it into a machine learner, and again looks what happens. 88% accuracy. That's even better than this one approach. But both approaches have a big disadvantage. And it's in the third column of both algorithms. It's a false positive rate. So false positive rate means, it's this one, 9%. And 30%, this means basically the rate of false alarms. So, in our case, 30% or 9% leads to several thousand false alarms per day. And this is completely unacceptable, actually, because every alarm has to be tracked by a security analyst, and we would drive these guys crazy, basically. So, we moved a little bit further down the road to a little bit higher advanced AI algorithms called deep learning. Deep learning is the latest development in neural networks, actually. And deep learners have several beautiful properties. One of the beautiful properties is they learn their features on their own if you give them the right data. The other beautiful property is that they can push down the false positive rate close to zero only if you give them enough data to learn. In our case, below 0.7%. That's result in a false positive rate around 50 false alarms per day, and this is acceptable. A deep learner basically setup looks like this one. You feed, from a top layer, you feed in the domain again, all the domains, imevil.com. you tokenize it, you convert it to ASCII code or something like this. Then you reduce a little bit the dimensionality through embeddings. You remember the very high dimensional stuff, the 54,000 in the previous example. And then you use one of the famous deep learning algorithms which are used today. Something like the LSTM or GRU. They are from the domain of recurrent neural networks. Recurrent neural networks are, for example, used for machine translation. So if you type in a Portuguese text into Google and you get an English text, you usually have an LSTM model behind this one. It's a so-called sequence-to-sequence learner. But you can also use something like a convolutional neural network. This is from the picture processing domain, actually, from picture classification. So all these applications like detecting incredible cute cats in YouTube videos go with convolutional neural networks usually. Something like this. You run it through a classification layer and get an output, for example, a sigmoid function where you classify, is it a DGA or not? A softmax function is usually used if you want to know which type of DGA it is. Getting one step deeper, we try to find out how it works actually, or if all the specific DGA algorithms we found around 64, 65 around from the database from the Fraunhofer Institute, it's a German research institute, they reverse engineered all the DGAs, let it run, and they give you a database how the created domains look like. So on the upper left side here is again the deep learner. On the left-hand side you feed in the domains. On the right-hand side you have 1 neuron per DGA type. And if you get an output here from the DGA type, the final layer, the final hidden layer inside this neural network has to contain the whole information. So we took this layer, mapped it to a two-dimensional space using a technique called multidimensional scaling, and looked if they are well separated. And you can see, yes, for example, DGA of type 1, here the yellow one, is far away from the other ones, here and here. Then you have, for example, the blue one, which is type 3. It's also very well separated. So the only one which is not very well separated is the green one here, and this is a special type of DGA, so-called dictionary-based DGAs. They use Google dictionaries or regular dictionaries to permute the words for building up the new domains and not shifting around letters like the code from Wikipedia I've shown you in one of the previous slides. Anyway, they can be handled by different deep learners, and you can fix this as well. So, we have to cope with other problems in a large corporate network like Siemens. Pedro already mentioned we have 60,000 events per second, which means we have to ask the deep learner 60,000 times per second, is it a DGA or not? And what type of DGA it is, for example. We capture 6.2 terabytes of data, and we do it 24/7, of course. There's always sunlight somewhere around the world, right? For this, we built a big, powerful platform on top of Amazon Web Services. We used only a subset of the Amazon PaaS services, so-called serverless PaaS services. These services have some properties where they are fully managed, they are auto-scaling, and they are auto-failover. We wanted to get rid of this task simply. We divided this whole platform into 3 zones: an ingestion zone, a storage zone, and a serving zone. The ingestion zone consists mainly of a Kinesis stream engine, and there we get the data in from Pedro's part, actually from the Flink engine. We pass it through to a landing zone. There is picked up by a glue engine. This is a managed Spark version, basically. There we do all the cleaning of the data, and we do the complex pre-processing, which is usually needed for machine learning, for artificial intelligence. From this point on, we move everything through our AI prediction system. It's mainly based on TensorFlow. TensorFlow is from Google. Somebody may know it. So maybe it's famous for, if you know it, probably from AlphaGo, that engine which has beaten all the world best Go players. So we use basically the same engine. It's open source. We enrich all the data inside here in the Athena database, and then these results are presented to our incident analyst or security analyst. These guys can use it either for better decisions, for faster decisions, or we create them certain alarms which then point them to certain types of attacks or, for example, types of DGAs or something like this. The security analysts are not only, actually a very important part in the whole platform here. They do not have only the task to find the right attack and somehow to contain it, but they also are a source of final truth for our platform, actually. So when they decide, well, let me say it this way. So when TensorFlow decides this is an attack of type A, and the security analysts decide, no, it's wrong, we feed back all this information back to TensorFlow, we relabel the data sets, retrain the whole system, and next time it won't make this mistake again. That way, we increasingly get better results in a nearly endless loop. Yeah. Thank you. That's it. So, any questions?
Hi. So basically, when you're using machine learning or something like AI, in security, you have to have the presumptions that you know what is good and what is not, and then you can teach the system how to distinguish between one of the other. Have you ever, how do you do that, and how do you prevent that the system learns something bad as good and then exponentially keeps you in a loop of keeping bad behavior over and over again, and then minimizing the efficacy of detection?
Yeah. Two possibilities. You have, like in every machine learning or AI, you have the possibility to use either unsupervised learning, so you train the algorithm to learn the normal state somehow, and then everything what deviates is usually something bad. That's one possibility, but it produces usually a higher amount of false positives. So the other possibility is, of course, you have the information in the data set what is good or what is bad. In that case, you need to have labeled data. So something like in the case of domains, you have a data set, this domain is good, this domain is bad, this domain is good, or something like this, and then you get usually a very low false positive rate. So if you do not have labeled data, you can only go with the unsupervised case, but in that case, you strongly have to rely on the specialists and have to keep them constantly in the loop that you improve the system constantly. They give the feedback, and that way, that's the same basically for the DGAs. So we constantly keep them in the loop. If we take them as final truth, if they say, no, that's not a DGA, but you said it's a DGA, we correct the whole data set and say, okay, retrain it.
So right at the end there, you were saying that you use human input to determine whether the end result was a true positive or false positive. Do you have any detections for false negatives?
Sure. So the statistics of getting all this information are there. I do not have it with me today, but if you're interested in, we can have a discussion on this later on. I have it for sure somewhere on my computer.
Hi, good stuff. Ricardo Morla from the University of Porto. I have three questions actually. How do you consider the adversarial nature of the attacker regarding the complexity of the DGA and an idea of the levels of your deep learning that the attacker may know? So can the attacker trick your AI system? And do you consider that? That's one. Second one is, do you have an idea?
Sorry, I didn't understand the first one fully.
No, okay. So can the attacker trick your AI system, basically? Did you consider that? And what are you doing regarding to that?
Yeah.
The second one is do you have an idea of how many DNS requests are not going in plain text and are going encrypted? So ciphered. So that means you cannot really use the AI to make predictions.
Yeah.
And the final one is I didn't understand, where are you using AI in other non-DGA, non-DNS domains in networking, for example? Thank you.
Okay, first one, can you trick somehow the deep learners? Depends on the way how they train them. So it's a task of the data science team here to make the deep learner somehow not memorizing all this information by generalizing. And then it's really difficult, because what we found out, that if you make this deep learners generalizing, they do not memorize the string simply, but they reverse engineer somehow the way how the DGA works. And that's what we found out. So in our training set, most of the DGAs we detect today is not available. So it's really, so they learn somehow the way how the DGA algorithm works. And there are currently approximately 65 different DGA types around, which are used actually. And if you bring a completely new DGA algorithm, they may be tricked. Definitely, yes. So then we need again to take the new examples in our database and retrain all that stuff. Second question was again?
Ciphering so there's DNS over HTTPS and other. So basically, how much do you know in your network?
Yes.
Where DNS is being used in plain text versus not? Maybe you don't know.
Actually, yes. So. Yes, if the text is ciphered, that's usually if you take the whole URL into account, not only the domain. The domain is usually not encrypted. But yes, so we had some experimenting with whole URLs where the whole content behind slash and all this stuff, arguments, is encrypted. Works as well. So for some reasons, obviously the structure of the encrypted text still has some properties which can be detected by deep learners. The hit rate is not as high as with the pure domain stuff, definitely. But it's helpful, at least for the analyst, to find out, it gives them a hint to where to point to or where to look to, actually. And the final thing is, did we do something, applied AI in other domains? Not very much right now. We actually, the plan was to first build up the platform, with this high-performance platform for this stuff. And we are going into new use cases like actually finding also communication to C2 host, which if it goes through, for example, Twitter or something like LinkedIn or something like this, and that would be a case like this one, there you have to take into account the whole URL information, the information which is usually encrypted, and find out if you can also get properties, if the deep learners can learn properties from exactly this string, as encrypted string, and point you to this one. Definitely a much more complicated task.
Thank you very much.
Welcome.
Hi. My question is, how long did it take to go from the old architecture to the new one?
Yeah, so I actually started that development during my master thesis, so it was 9 months. It was to develop a proof of concept in order to replace our current infrastructure. So we were able to set up Kafka, we were able to set up our collectors, and we were able to set up the rules engine in just this interval, right? So took about 9 months for this first POC, and then more 9 months around, more around a year, just to fine-tune stuff, to improve the language, and then the operational stuff, like if something is down or if there is a problem with the architecture, we need to detect it. So
Thanks.
around almost 2 years. Yeah.
Hi. Thank you for the talk, but I need to know one thing. Do you mark a bad domain or good domain only by the URL or by the content of the domain?
Only domain.
Only
domain, not the URL. The URL is a different case, actually. There are two reasons for now not to use the whole URL. One reason is that there are not really good data sets available for the whole URL and stuff. It would be necessary, actually, for example, for the case that the communication goes through Twitter, through LinkedIn, through Facebook, or something like this. I would like if have such a data set, and there is a DGA data set which is available, or multiple DGA data sets which are available. They are labeled. So the labeling is usually the most expensive task in machine learning. So if you don't have it, you have to do huge efforts, actually. Wow. Should I dance now? No, okay. So labeling, you can, if you don't have some kind of source without labeled data sets, you do need to do the labeling yourself with simulation, with help from other people and all this stuff, or even buy the data sets. And the second reason, simply, it was not necessary for this data set. The domain was completely enough.
Thank you.
Hello, thank you for this presentation. If I understood correctly, your system is able to detect the pattern that generated the domain. But how does your machine learning deals with domains that are not good, but are just random words from English? This means that the domain is not generated, but it's just random words put together, and therefore are not generated. How the system deals with that?
Sorry, I didn't understand fully. So what do you mean? What type of?
Yeah, when the domain is just random words, like 4 English words, how does the system deals with these kind of domains? When they are not a pattern, when they are not generated. Because if I understood correctly, your system detects the generation algorithm, the pattern of the generation, right?
Yeah.
And if the domain is just words, like simple English words, how does the system deal with this?
Yes. So that's one. So then also this was one of the actually initial problems with the system. Of course, that if you have permutation of regular words, they are not very well detected. But at the end, you can also use for the machine learners dictionaries where they know actually the patterns from the words. Or you can combine it with an ensemble approach with other learners like fast text or something like this, and you use in one ensemble approach a deep learner together with a text specialized learner or something like this. So what we do in that case usually.
Okay, thank you.
Well, let us thank the speakers.
If you can, I would like to ask a question also. I can. The question is, there are some DGAs that have different, it's the same DGA, but uses different seeds to initiate the DGA algorithm.
Yeah.
And the question is if the system is able to detect separate seeds of the same DGA.
The answer, yes. The training data set we use for the deep learners, we didn't know actually which seeds have been used by the attackers. actually. So what you get from the database, for example, from the Fraunhofer Institute database as data set, they reverse engineer 60 types of DGAs actually. They used some kind of random seed, and this is definitely not the seed which is used by the attackers we have seen. Anyway, the deep learners, and that's one of the beautiful properties, could reverse engineer somehow the algorithm, and somehow it detects also DGAs with a completely different seed. So that's a little bit a downside of a deep learner. It's not really known how they work internally, but they did, and these results you have seen on the board, okay, that's a 0.7% are done with seeds we haven't seen before.
Thank you.
Any more questions? So let us thank the speakers, please.
Thank you.